All right, so let's take a look at molecular compounds. Um, in Unit 5, we talked about the reason why atoms bond together. They want to fulfill the octet rule, or in other words, they want to have a full outer shell of electrons. There's two types of bonds that we're going to learn about. We already did ionic bonds. That's where you have a transfer of electrons. One ion, the cation, loses electrons, the anion gains electrons, and then they're attracted to each other. These bonds occur between metals and nonmetals. This unit, we're going to be talking about the covalent bond, which is a sharing of electrons. This generally happens between two nonmetals. And as you can see, a third metal called a third type of metal, a bond called the metallic bond, occurs between two metals. We're really not going to focus on that in this class. Okay, so let's just review a little bit. What is a compound? A compound is a pure substance made up of two or more elements chemically combined. And the molecule is the smallest unit of a compound that retains the properties of that substance. Now, we can't separate the atoms from each other unless we have done something chemically. So a molecule cannot be separated physically, only chemically. Most of the time, a molecule is a compound made up of more than one type of atom, but there are a few elements that actually only exist as molecules because they can't exist as one atom. They have to combine with something else, and so the elements here that you see, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and sulfur, when they exist in nature, they exist as molecules. Although remember the term homoatomic, they're homoatomic molecules, and so they still are considered elements. So a compound formula just lists the symbol of the elements involved and how many there are as a subscript. So carbon monoxide means there's one carbon and one oxygen. Water means there's two hydrogen and one oxygen. Ammonia has one nitrogen, three hydrogen, and so forth. All right, and again, a review. Diatomic molecules are those that have two atoms. They could be the same or they could be different. If they're the same, they're homoatomic molecules. If they're different, they're heteroatomic molecules. You can have triatomic molecules, which have three atoms, or polyatomic is what we use if there's more than three generally. All right, so a covalent bond, as I said a little while ago, is a sharing of electrons. So, like for example, when fluorine bonds with itself, one fluorine is not going to be able to steal an electron from another. So the only way that they're going to be able to get 8 electrons is if they share a pair of electrons. And just to keep in mind, when electrons are shared, they are shared in pairs. So a bond is two electrons, which we call a shared pair. And in this case, that pair gets counted for both elements. So if you're looking at the molecule of the fluorine, you can see that the fluorine on the left has 8 electrons if you count the ones that are shared, and then the fluorine on the right also has 8 electrons. You also count the ones that are shared. So this is why a molecule will create a covalent bond. What's happening? The simplest covalent bond is a hydrogen bond because each hydrogen has one electron and they each want to have 2. So the hydrogen is really an interesting atom. It can do a lot of things, but in this case, it's going to make a covalent bond by sharing that pair of electrons. What happens is as the atoms get closer and closer to each other, the electrons end up attracted to both nuclei of the two different atoms, and so they're held in the middle of the two neutrons. They're attracted to each side, so they're held there in the center. we can sometimes we use a shared pair as a bond, but more often than not, you'll see that if you see a dash between two atoms, that is a bond between two atoms, and every dash it represents a pair of electrons. So every dash is two electrons. Um, So we can, as we just saw, we can share electrons between identical atoms. So those elements that we said earlier, nitrogen, oxygen, fluorine, chlorine, etc. They are formed when an electron sharing occurs between identical atoms, or we can also have molecules that are heteroatomic and there's sharing between different atoms. So here you can see some examples of molecules. We're going to talk more about the shape later in this unit, but you can see that the carbon is bonded to two oxygen and carbon dioxide. Water is one oxygen bonded to two hydrogen, etc. All right, so how can we tell how many bonds an atom wants to make or is going to make? So remember that in the last unit we were able to look at the periodic table and could tell when the elements gained or lost electrons. Well, it's going to be sort of in the same way that we can figure out how many bonds an atom can make. So again, remember that they share electrons in order to get a noble gas configuration. So they want to fulfill the octet rule. So they want 8 electrons. So different atoms are going to need different numbers of bonds in order to get those 8 electrons. All right, so hydrogen, as we just saw, only has 1 electron, and it needs 1 more electron, and so it will form 1 covalent bond. Similarly, all of the elements in group 7A have 7 valence electrons: fluorine, chlorine, bromine, iodine. They are 1 short of a full octet, so they really only want 1 more electron, which means they're only going to form 1 covalent bond. This is important when we start putting the molecules together, because elements like hydrogen and fluorine can't be in the center of a molecule because they can't make more than 1 bond. Oxygen, which is in group 6A, has 6 valence electrons, needs 2 more, so it will form 2 covalent bonds. Nitrogen and those elements, or those nonmetals in group 5A, have 5 valence electrons and will form 3 covalent bonds. And then the nonmetals in group 4A, carbon, silicon, have 4 valence electrons, and so they will form 4 covalent bonds. Just as a side, some of those, if you're the elements that are in the 3rd row or lower, things like phosphorus, sulfur, chlorine, bromine, they actually can have more than 8. So they can have different bonding patterns, and it has to do with d electrons so they're not really following the octet rule. They can hold more than 8 electrons, but only if they're in the 3rd row or below. So here are some of the exceptions to the octet rule that you want to keep in mind. Since hydrogen only needs 2 electrons to fill its outer shell, again, it's only going to make 1 bond because it only needs 2 electrons. Boron is a little bit unusual. It only has 3 electrons, so it can only make 3 bonds. It's only really going to have 6 electrons when it forms its molecule. Now, it does have some other kind of conditions where it might accept other electrons in some other way, but as a straight molecule, boron will only have 6 electrons. And then, as I just said, atoms in the 3rd period or lower down that have empty d orbitals can often accommodate more than 8 electrons. So phosphorus, for example, can make 5 bonds. Xenon, which is already a noble gas, you would think, oh, it can't make any bonds. It can actually make some bonds. It can hold up to 12 electrons. But just keep in mind, we're not going to be covering those that have more than 4 bonds in this class, but there are some out there. Didn't want you to think I was lying to you or anything. All right, so this is a nice little chart that just tells you how many bonds each element can make. So Again, in group 1A makes one bond, well, hydrogen. Boron can make 3 bonds. Carbon, silicon make 4 bonds. Nitrogen and phosphorus tend to make 3 bonds. Oxygen and sulfur tend to make 2 bonds. Fluorine, chlorine, bromine, iodine tend to make 1 bond. However, you can see some of the ones in parentheses. They can also make 3 or 5 bonds, and sulfur can make 4 or 6, and phosphorus can make 5. And then even xenon can make some bonds. So let's look at these compounds and determine if they are logical molecules, if they're likely to exist. All right, so if we look at A, we see carbon bonded to 3 bromines. Well, the bromines are good because they only make 1 bond. So each of those bromines are good. But carbon needs to make 4 bonds to be stable. And so CBr3 will not be a stable molecule. It would have to have 1 more bromine or some other element. ICl is a reasonable molecule because the I and the Cl both each need to make 1 bond. So they each have 1 bond. C would not be a stable molecule because, no, the hydrogen are fine. Each hydrogen can make 1 bond, but fluorine can only make 1 bond as well, and so it's not going to bond to 4 different hydrogen. SH2 is a reasonable molecule because sulfur can make 2 bonds. All right, so there's your answers. All right, so let's just look a little bit more at the structures. What we're going to do in the next few slides are draw Lewis dot structures of molecules. And so it's going to, a Lewis dot structure is a representation of how the molecule is bonded, and it shows both shared pairs of electrons, which we represent with dashes, and unshared pairs of electrons, or sometimes they're called lone pairs, that are just shown being attached to 1 atom. So these are examples of Lewis dot structures. They are very useful in a lot of ways. They are limited in some ways, which we'll see later, but they do show how elements are attached to each other. So what I'm going to do in the next little while is to give you the rules and tell you how to draw Lewis dot structures. But I just want you to keep in mind that I'm not going to ask you to draw a Lewis dot structure from scratch. I want you to be able to look at a Lewis dot structure and understand what's happening, how many bonds there are, how many lone pairs, things like that. So I want you to understand it. Sometimes drawing them from scratch are a little difficult because you may not know what bonds to what. But what I'm going to do is go through a few worked examples and the steps necessary to get the Lewis dot structure. And again, I give you the steps, don't memorize them. You can follow what I'm doing, but I'm not going to ask you to do that. So at the end, I just want you to be able to look at a Lewis dot structure and determine how many bonds it has, how many unshared pairs, etc. But I think it's worthwhile to go through the Lewis dot structure process so you can see where they come from. All right, so here are the rules, and I'll just briefly go through them because I'll go through each step when I go through some examples. But of course, we want to know the molecular formula, so we'll know how many of each type of atom there are. We need to know how they're connected to each other, how the atoms are arranged. We need to determine the total number of valence electrons available to the molecule. We'll do an example of that in a minute. Then we distribute the electrons among all the atoms. The way that we do that is we put a pair of electrons, or in other words, a bond, between each of the atoms, and we subtract 2 electrons for each bond that we make. And then if we have any extra electrons, we want to give all the outer atoms enough to make sure that they have 8, or in the case of hydrogen that it has 2. And then if there still are any extra, we give them to the center atom. And if all the atoms then have the correct number of electrons, you're done. But if some don't have enough, we're going to have to do what's called a multiple bond. And I'll show you an example of that when we get there. All right, so first what I want you to be able to do, and you do need to be able to do this, how to determine how many valence electrons are in a molecule. Well, we talked about this in the last unit. You can determine how many valence electrons any atom has by looking at which group number they're in. So group 1A has 1 valence electron, group 2A has 2, group 3A has 3, etc. As long as you're looking at the A group numbers. So if you want to find out the number of valence electrons that a molecule has, you just add them up. So for example, CH4, we would look at carbon. Carbon has 4 valence electrons because it's in group 4A. Hydrogen is in group 1A, so each hydrogen has 1 valence electron. So if we add them all up, we have 4 plus another 4, or 8 valence electrons in this molecule. All right, so let's continue on with CH4 and show how we would draw the Lewis structure. So step 1, the formula indicates there's 1 carbon and 4 hydrogen. Step 2, you use the connecting pattern. That's often the hardest part, but that, here I'm just gonna, you'll just have to kind of take my word for it. But also keep in mind, a lot of times this is determined by the number of bonds that we know elements can make. So we know hydrogen can only make 1 bond, so it can't be in the center. Carbon can make 4, so it's likely that it is in the center. But anyway, I'll always show you the connecting pattern. All right, now this molecule has 8 valence electrons, like we just saw. So in the next step, what we want to do is distribute those electrons and use them all up. So the idea is sort of, the C's and the H's all come together, and all together they have 8 valence electrons, and what they want to do is arrange them in some kind of way so that they all are satisfied. They all satisfy the octet rule. So in other words, carbon wants 8 and each hydrogen wants 2. And so it's sort of like a puzzle. They have these electrons. They can't use any more or any less than what they have, but they have to use what they have and arrange them so that everybody's happy. So in this case, what we're going to do, so we have 8 valence electrons. If we make a bond between each C and H, we use up 2 electrons for every bond. And so in this case, to bond the C to all 4 H's, we use 8 electrons. Well, we have 8, so we use them all up. All right, so far so good. Then we just want to go back and make sure everybody has what they want. Each hydrogen has 2 and the carbon has 8, so we're good. We've used up all our electrons. We don't have any extra, and everybody is satisfied. They have the number that they want. Again, you can see on the left that we use the pair of electrons to show the bond, but more often than not, you'll see the molecule shown as it is on the right. All right, so let's now draw the Lewis structure for H2O. Again, the formula indicates there's 1 O and 2 H's. The connecting pattern has the O in the center, mainly because hydrogen only can make 1 bond, so it's going to be on the outside. All right, now how many valence electrons does water have? Well, oxygen is in group 6A, so it has 6 valence electrons. Hydrogen is in group 1A, so they each have 1. So there's, again, a total of 8 valence electrons. So now the idea is to arrange those 8 electrons so that oxygen has 8 and each hydrogen has 2. So to do that, we're going to first bond together the O's and the H's. So if I draw a bond between the O and one H, I've used up 2 electrons. If I bond the O to another H, I've used up another 2 electrons, so a total of 4 electrons. So I've used up 4, but I still have 4 left. When you observe the molecule, you notice that each hydrogen is now satisfied because they have 2 electrons, but the oxygen only has 4 electrons. It needs 4 more. I have 4 more to give it, so what I do is I just give those 4 electrons to the oxygen, and you can see on the bottom that the oxygen has 2 bonded pairs of electrons and 2 unshared pairs of electrons. So those dots belong only to the hydrogen. Those dots are very important, as we'll see later in the unit. They have a lot to do with the shape of water, and so that's why it's really important to see what's happening on the molecule. But again, we had 8 electrons. We've distributed those 8 electrons. Each hydrogen is satisfied with 2. The oxygen is satisfied with 8, and so our molecule is complete. I just want you to, one thing to keep in mind is, like I said, electrons like to stay in pairs. So when we make a bond, usually we draw a dash. Usually we represent the unshared pairs as a pair of electrons, 2 dots, but do keep the dots together. So notice how there's a nice symmetry here. We've got 2 on the top, 2 on the bottom. So electrons like to be together. If you don't have all pairs, an even number, then you've done something wrong. All right, so let's look at another example, PCl3. Again, the formula indicates that we have 1 P and 3 Cls. The connecting pattern puts the P in the middle. P can make 3 bonds and Cl can only make 1 bond, so that makes sense. If we find out how many valence electrons we have available to this molecule, phosphorus has 5 valence electrons. Each chlorine has 7 valence electrons, so we have a total of 26 valence electrons. 21 from the chlorines and 5 from the phosphorus gives us 26. So again, we're going to distribute those 26 electrons to try to make sure that all the elements, in this case, they all need to have 8 electrons. So the way that we start, again, is to make our bond between elements. So if I bond the phosphorus to each chlorine, I've used up 6 electrons. So I still have 20 electrons left. The next thing I do is I put electrons around the outer elements to make sure that they all have 8. So in this case, each chlorine needs 6 more electrons to have a total of 8. So if I give each chlorine 6 more, 3 times 6 is 18, so I've used up 18 more electrons, and now I have 2 left over. So I've distributed 18 out of my 20. I've distributed 24 out of my 26 electrons, 6 in the bonds, and then 18 around the chlorines. All right, now we can see by inspection that each chlorine's happy. We just gave it 8, each one of them 8. But the phosphorus still only has 6 electrons. It wants to have 8. We have 2 more, so they belong directly to the phosphorus, and so you can see the Lewis dot structure there on the bottom. Phosphorus makes 3 shared pairs of electrons, 3 bonds, 3 shared pairs, and phosphorus also has 1 unshared pair. We will continue more of these Lewis dot structures in the second set of slides. Okay.